I'm Björn. I want to talk about configuring Prometheus for high performance. Who am I? It's written on my GitHub profile here. I'm a Prometheus developer and a SoundCloud engineer, more or less. I was not with the project when it was started. I'm not one of the legendary founders, but I have been there for long enough that I was working on it before it was cool. And honestly, I had no clue this would become the mainstream monitoring system of our times or something. It's like it has many entrance barriers in a way. It's kind of complicated, completely new concepts. But one thing, and I think this is one of the reasons why it's now here and we have packed rooms, it's operationally really simple. It takes literally minutes. You get a Prometheus server running, you monitor your node exporter or your Prometheus yourself. I do this literally in minutes, in demos. So people get something meaningful doing and then they take it from there, right? Now this is not an introduction talk, it's an A. In German means Anfänger, but in English means advanced, I guess. So you all are super advanced Prometheus users and you are all here to know about operational problems if you want to get really high performance out of your limited resources. So I don't want beginners in this talk because they would be scared. It's actually quite easy in the beginning, but if you do something really crazy, then it becomes more complicated. I also assume you know all the best practices, right? Don't go crazy with your serious cardinality. Like SoundCloud likes to put the user ID in the metric, then you have 350 million metrics or something. Use recording rules for fast queries, and all of that, you got that, right? Right? Okay, so this is about how do you tweak your Prometheus configuration to get the best performance out of it. Most of those tweaks are just command line flags, and like every reasonably behaved Unix command, you can just run Prometheus-H and it gives you the flags. Whoosh. That's not even all of them. Like we have 46 flags in 1.5.2. Luckily, we namespaced them, right? So it's a bit weird, but it's helpful if you have many of them. And most of the tweaks are related to the local storage. And if you color them, these are the flags that start with storage on local. They are only 17. So that's like, it's like shock therapy, right? First you see 46 and then you're 17, easy. But 17 is still a lot. And I mean, I'm to blame for that. Also, this guy, Julius, he's one of the real founders. Is he in the room? Perhaps he ran away, I don't know. Perhaps because I blame him now. Okay, so back when Prometheus was created, like 2012, it was a prototype. It had a prototypical storage layer, storage v1 if you want, and Julius realized this will not pull it off if you do the real thing, so he started to write storage v2, as we call it now. So he's to blame for the fundamental design. I kind of joined the effort, and then I took over, and now I'm the de facto maintainer. Also, like most, if you, like 2013 storage, 2014 perhaps, 2015 was public launch, now we have 2017. So most of the lifetime of Prometheus, it had this storage. It kind of has aged and not always gracefully. You run into more and more corner cases, you realize, okay, we have to optimize that, and sometimes you cannot just clear cut, use it, make it the one way. You have to ask the user for a trade-off between data safety and performance or something. So one flag came to another, and here we are. So the best way to understand flags is from first principles. That means you read the code and you understand what the flags are doing, right? If you don't have the time, but you have like half an hour to spare, watch this talk by this person in the other Prometheus. Also it needs more views, right? So this will explain how storage v2 works in principle, and then it also explains the flags from first principles. This talk is not the other talk, so this is more like, let's talk about practical ideas how to tweak your flags. There's also a nice page, this is more like man page style or cookbook style, on our awesome documentation site. We get loads of questions about storage tweaking on the list, or just memory usage and things like that. Like people ask on IRC, on the mailing list. And then I point them to that page, and I point them to that talk, and then they should be completely satisfied, but for some reason they aren't. And this is kind of how the idea for this talk was born. It's kind of audio FAQ or something, right? Okay. Let's start where you all started. You spin up your first Prometheus server, you let it run, and since you're all advanced Prometheus users, and general, like, you have the right operational attitude, you monitor your Prometheus user. guess what monitoring system you would recommend? Prometheus, right? So, okay, you can graph things. This is a graph of the memory usage of a Prometheus you have just started up. There are many lines. The green one is RSS, resident segment size or something. Broadly speaking, kernel developers will kill me now. This is essentially the physical memory your process actually takes. Then we have the blue line, which is the heap space as seen by Go. Heap space as seen by Go is objects on the heap that are still in use and objects that are not in use anymore but not yet collected by the garbage collector. Okay, so the blue line is super noisy, and Brian, who sits, has told you something yesterday about counters. This is not a counter, it's a gauge, and you have exactly that problem. It has peaks all the time, and even Prometheus doesn't get all the peaks because it might scrape your other Prometheus server every 15 seconds, and then Grafana samples it down. So there's a purple line, this is max over time for 5 minutes, and the other purple line is min over time. It's Brian's idea. So this helps a lot to see that there are actually like maximums happening all the time. In reality, peaks could be even higher. So my suspicion would be that we have a huge peak here and that drove up the RSS. But the RSS is weird, right? We will talk about that later. So you see this, whatever the curve is, all goes up and to the right. So this is clearly a memory leak, right? So you wait for a while, and then you oom. And what do? You go to GitHub, you file an issue and say, yeah, your kind of glorious monitoring system you might not have noticed, but it has a memory leak. I have noticed. Perhaps, yeah. Perhaps not. So if you have enough memory and you wait for a while, it looks like that. So you get a steady state at some point. Cool. Question is, what determines where this steady state is, right? And that's actually super hard to answer. There are so many moving parts in a Prometheus server. Even things like service discovery might be quite memory hungry. Then you have to retrieve samples from the discovered targets. You have to ingest them. You have to index them. Indexing is via LevelDB. For us, it's just a fairly established library, but for some reason, sometimes it takes weird amounts of memory. Then we have queries, of course. Queries sometimes take a weird amount of memory. And then we have our actual raw sample storage v2, which we understand quite well, but which also takes memory. They allocate memory, they free memory. And for some reason, you get this blue curve, and then the Go runtime requests memory from the operating system, and the operating system does something, and you get this weird green line. It's kind of hard. But there's one lever you have to move as a user. It's your responsibility. As advanced user, you have probably seen it because this is the one flag you cannot ignore. Storage local memory chunks. What does that mean, chunks? The memory, the raw sample storage is chunked. So we have 1 kilobyte fixed size chunks where we put the samples in with a compression, so we get many there. And then a series of chunks is a time series, and we write them out to disk with the same layout. So we have chunks on disk and chunks in memory, and we can now just mirror them to disk and load them back if needed. And we want to tell Prometheus how many chunks can be memory, and this is this number. It's like 2 to the 20th or whatever. Like it's a million, essentially, a mega chunk. That's the default value. For bigger servers, that's not enough, and for smaller servers, that's too much, and you will just oom by default. So those memory chunks, there are different populations. There are the chunks that are still being written. We call them head chunks. They are not even done, so you can't write them to disk because they're still changing. And then there are chunks that are done, but not yet written to disk. They are called chunks waiting for persistence. And then there are chunks that are written to disk, but still lingering in memory because caching is good, right? Okay, and whenever your number of chunks in memory goes beyond this number, Prometheus will kick out those chunks that are already written to disk. Least recently used, how caching works. Of course, it might happen. You have too many chunks that are not yet written to disk, or are not yet completed, or a query uses them at the moment. This is also a condition where you cannot evict them. And then this number would go over that number, and your memory would explode again. But Prometheus at least tries to protect itself, and then it stops ingestion, which is something you don't want to have. You have probably into this. Okay, so how to avoid stopping ingestion? You want to tell the server to persist chunks more quickly if you get closer to that point. And that's why we have another flag. At some point, we realized we need to add another flag. So this tells the Prometheus server how much chunks may be in that state where they're waiting for persistence. So we specify that so that Prometheus knows if we get close to that value, we have to speed up how we persist to disk. Of course, you might ask, why aren't we speeding up persistent to disk all the time? Like, why not best effort? Just write to disk as fast as possible. This is a good question. It's explained in detail in that other talk, just very short. Disks are hard, right? And spinning disks are hard because they take eternally to seek to that file on disk where we write our chunks to. So we have one file per series. You want to write chunks to the end. You seek there, it takes 10 milliseconds, right? 10 milliseconds is like endless. And then you write one chunk. And then you seek to the next series, again 10 milliseconds to write a single kilobyte. This throughput is like ridiculous, right? That doesn't work. So you need to batch up writes. You need to save a few chunks in memory before you seek to that point on the disk and then write like 4 or 10 chunks or whatever. Okay, SSDs solve all problems, right? So they don't have seek time, so we can just write tiny amounts all the time, right? No, wrong. Because SSDs hate if you write a single kilobyte. Like, at least they want to write 4 kilobyte. Bigger SSDs want to write 16 kilobyte. This is their page size. If you don't do this, you get write amplification. It's super horrible. You also burn through the lifetime of your SSD. So definitely, whatever you have, you want to batch up. So this is why you don't want to write at full speed all the time. You want to batch up as much as possible. So you have to tweak those numbers. So Prometheus has a nice metric called the persistence urgency score, and that's actually exported by the Prometheus server. You can plot it in Grafana, you can alert on it. So this is essentially how quick Prometheus wants to persist. It's calculated from all those numbers that are also exported as metrics. So max chunks to persist is the limit you've configured. Chunks to persist is the actual number of chunks that are waiting for persistence. This is our memory chunk flag, and this is the actual number of memory chunks. You can plot them all, nice curves. And essentially, the urgency score is chunks waiting for persistence divided by the maximum allowed number to wait for persistence. And sometimes you see these funny messages, right? Storage has entered rush mode, chunks to persist, big number, something, something, big number, something, right? So now you can kind of guess what it means. So we have all those numbers here. And you see chunks to persist is 12 million, max chunks to persist 50 million, so this is 0.8. You can see how this works. And what is rush mode? So rush mode is if the urgency score ever hits 0.8, then Prometheus thinks it's not just enough to be gradually faster, we have to do like desperate measures now. So it does things like, now we go as fast as we can. We also don't do like early checkpointing, which is a different concept. And we also don't insist on f-syncing every single file anymore if we write it. Usually, I mean, people often think this is super evil, and they like write FAQs. So my server goes into rush mode all the time. What can I do? It's actually not super evil if it helps. So this, you can plot this in your dashboard. If it hits 0.8, it should go down again. So at some point, it will hit 0.7, and then you leave rush mode, and all is good. If this happens sometimes or even periodically, fine. What should never happen is you reach 0.8, you go into rush mode, and the urgency score goes up and up and up and up all the time. Then you are in trouble. Predict linear, by the way, comes in handy if you want to alert on that. If you really hit one, something bad happens. But I want to show you this one more flag. So people have, like, it depends on context and also on religious beliefs if you want to sync files or not. So this is also configurable. This is a trade-off we can give to the user. The default of this flag is adaptive. That means don't sync in rush mode, but sync in non-rush mode. You can also say never if you don't believe in syncing because you want to use the page cache and everything, say never. And if you think you should always f-sync, it really depends on circumstances. Longer discussion, 3 other talks could be given about that. You set it to always. Okay, so this has happened if you're rushed, if your urgency score ever hits 1. It also tells you the reason. So in this case, it's because we have hit the max chunks to persist. It could also be the other way, that your memory chunks go up too much, perhaps because you have queries that pin too many or other reasons I'll talk about in a second. And it even tolerates 10% more than the configured value, but then it also gives you this dreaded message, ingestion is throttled. This is horrible for various reasons. We don't even need to discuss that. You should definitely avoid that. If that happens ever, or even like more than once, you should do something. Okay, so now what are the right values for those flags on a real server? Naively, you might think, okay, a chunk is a kilobyte. I said that. So a million chunks is a gigabyte. Easy, right? So let's say we have 64 gigabyte and like half of it for chunks, 32 million memory chunks. We can set this, done, right? No, it doesn't work that way. Prometheus is doing so many things that you have to do this way lower. Yeah, I mean, I already talked about like level DB, queries, whatever. All those things take memory. So this is way lower than you expect. Many factors in the equation. And if you look back at this thing, so the green line should never cross the memory you have, right? So let's, I don't know, whatever. Let's say like our real memory is here, and this peak was already quite dangerous. You should never go higher than that. Now, this line is kind of what we, what Go thinks it uses. So this is already lower, and even this ratio is kind of hard to predict. My rule of thumb is this peak is probably 2/3 of this peak. This is not always true, but it's kind of a conservative estimate. So let's say this line is 2/3, but then you get this up and down, right? That's just natural. If you see this is 7 gig, this is 14 gig here. This is a factor of 2. This is not coincidence. This is how Go garbage collection works. You have a heap size where the garbage collector was done, and then the garbage collector waits for the heap to double in size, and then it runs a new garbage collection cycle. Easy, right? But that means if this is the line you cannot cross, it's 2/3 of your RAM, and the baseline you have with your garbage collector is this. This is half of 2/3 is 1/3. So essentially, only 1/3 of your memory is available for all the chunks you have allocated all the times and all the other things that might be allocated all the time. So this is where this factor of 3 from the documentation side comes from, but this is really a lower bound. Some people try that and then they So what we do at SoundCloud, this is from our original Chef recipes because we are like old school and deploy Prometheus on bare metal with Chef. So this is what we do. Like Chef has memory in kilobytes. We divide it by 6. So a sixth of our storage is essentially used for memory chunks. But you already see, like there's a comment here. This is a rule of thumb, works in 90% of the cases. Sometimes it's super wasteful. If your Prometheus server is actually not doing so much else, you're not making use of your memory. You're wasting a lot. Or it's the other way around. It's actually doing a lot of other things, like has a lot of series, and then it has to manage individual series, has big indices, has big service discovery. This might not even be enough. So this works most of the time. You can try that yourself, but sometimes you have to tweak it, which is not a good situation to be in, but yeah, manageable. And then the other question is, max chunks to persist. What's a good value there? We just use half of the other value. In general, good idea, but it again depends on things. If you really want to batch up a lot, then you want to have this as high as possible. But on the other hand, like if you have many time series and every time series has this head chunk that cannot be evicted already, you don't want to have too many chunks in this population because then you might again because too many chunks here. So this is always smaller than this one, obviously, but the number is smaller. I would start with half of it, and then you can tweak it. We have also written this into our Chef recipe that people can tweak it. This is all valid for 1.5 to 2. 1.5 in general, but the other one are buggy, don't use them. 1.4 was way more erratic in memory consumption, and it was also way more wasteful for various reasons. Sometimes it was just a mistake, sometimes it was a trade-off between query performance. But Brian, who I mentioned a couple of times, and you have heard the keynote, and he also sits here in the first row. This is him, in case you didn't notice. So he did a lot of research post 1.4, which went into 1.5, how you can actually make this a bit more even and save a bit more memory. So that was great work, and it already simplified many things. He wrote a super awesome blog post on his company's tech blog as like fallout of his research. And this is funny enough, it's exactly the opposite question than we have at SoundCloud. So at SoundCloud, we have our bare metal servers, and we think, okay, this is your team's Prometheus server. You want to get most performance out of it. So use these settings and tweak at will. But in many other situations, it's the opposite. You know, I have 2 million metrics, and I want to ingest 100,000 samples per second. So what EC2 instance do I have to order? Or what container settings do I want to have if I run my Prometheus server like on Kubernetes or something. And that's all explained in the blog post. I wouldn't even go into all the details because it's way too sophisticated. But you can try this out. Like, of course, again, you use Prometheus to monitor Prometheus. And these are the queries from the blog post. So the first one explained in the blog post, just broadly speaking, this is the number of chunks you actually create in 6 hours. Because 6 hours is the sweet spot that Prometheus wants for matching up the writes, right? And you can do this with a few factors, all explained in the blog post. And this is just example. Let's try it out. On a beefy Prometheus server at SoundCloud, it's 6.8 million chunks. You want as chunks to persist to have a 6-hour cycle for batching up, right? And then the heuristics here to increase how many more memory chunks do you want is actually the number of series. Rational is kind of, these are the head chunks you have at least. So you take the maximum of memory series you have, it's 4.6 million, pretty beefy. It's already kind of hard to run a Prometheus server that hot. You get 4 million for that, and the total number is 11 million. With our divide by 6 rule, this will probably not fit on a 64 gigabyte machine. It depends, right? If you don't do many other things, it might totally fit. But if you do many other things, expensive indices or something, it might not fit. The server I took this from is a 64 gigabyte server with like hand-tweaked parameters. And these are actually the parameters we used without knowledge of Brian's blog post. So you see they are way lower, and that's because on that server we would just oom with those settings. And this also means we are not in the comfort zone that Brian's blog post puts you in, right? Brian's blog post is like, yeah, we will probably never go into rushed mode. You have lots of headroom for peaks and stuff. This is like we run it as hot as we can, right? This will go into rush mode occasionally. It kind of works. This is a production server. But yeah, this is how you see you have a bit of leverage between super conservative and run it bleeding edge. All right. So what is the basic problem we have here with all those tweaks? The basic problem is we have all those factors that vary. Like I talked a lot about the number of series you have currently in memory. And you have so many things that might or might not take memory. So yeah, it's hard. It would be so much nicer if you could just tell Prometheus, please take that amount of memory and do the best. Like, yeah. So 1.6, we should have totally released that on the first day of the conference to get super confused with Kubernetes 1.6 being released at the same time. Anyway, this has a new flag. It will be released next week or something. So you can actually tell Prometheus the target heap size. You can't tell Prometheus RSS because Go doesn't even know the RSS. But the upper purple line, that's essentially what you can clamp Prometheus at. It's not rocket science and might still have little peaks going over that. 1.9, Go 1.9 might help us to implement that better. But that works, right? This is like 2 gigabyte. You can now tell Prometheus, now, next week, or build from master, please use whatever, 30 gigabyte of heap size. And it will try to make the best out of it. You can't even see how that works. I screenshot my mouse cursor, I'm sorry. So this is what you have. You have 1.5 million time series usually, but then the crazy team that has so many instances on their Kubernetes cluster, they decided to redeploy everything. Suddenly you have all the old time series, still a memory lingering somewhere with chunks, and you have more time series. And then this is actually an 8-hour shift, and it already goes down again. But often you have this, oh my God, the deploy was wrong. Let's just redeploy everything again. And then within 10 minutes, you have like triple your time series. And that's usually either you're super conservative with your settings, and the chunks stay all the same in 1.5, but now you have more time series to manage. You either oom or your settings are super conservative, and in usual cases, you don't actually use your memory. This is now the new thing. You see, like the blue stuff are the head chunks that are open. The orange stuff are the chunks that are waiting for persistence, and the green is just the caching. Okay, and you see it jumps up, and then Prometheus kind of counteracts. Something happened here, I don't know what. Expensive query, level DB compacted, or I don't know what. Something needed more memory, so Prometheus reacted, evicted like the cached chunks. And here's the other jump, which apparently was heavy on the memory, so it evicted a whole lot of chunks. So this works like a charm. Pretty good, saves you a lot of operational trouble. Okay, what it doesn't change is checkpointing. What's our time? Okay, a few minutes. Checkpointing is my next biggest enemy. So what is checkpointing? If you watch the other talk, you will understand. I will explain it super quickly. You have all those chunks that are not yet written to disk, and you have all the open head chunks, and now you want to shut down your server. So where do they go? You could like stop ingestion and wait until they have been all written to the individual files. Will take like 6 hours, but yeah, or perhaps in rush mode bit for shorter. But you don't want 6 hour shutdown time, right? So what you do, you write a gigantic blob to disk which has all the non-persisted parts in one big file, because writing one big file is way easier. And ideally, this takes like 15 seconds, but you scale up your Prometheus server, you buy more RAM, you buy bigger disks, it's all possible, but what never scales up, or almost not, is the speed you write to disk. So if your checkpoint is twice as much, twice as big, because you have twice as many series, it takes approximately twice as long to write. At some point, on beefy servers, your checkpoint takes 10 minutes, 50 minutes, gets pretty horrible, right? By default, we checkpoint every 5 minutes, not only on shutdown, but also regularly, because your server could just crash, right? And you don't want to lose too much data. So this is like a conservative setting. Don't lose more than 5 minutes of data. But if your checkpoint already takes 50 minutes, you are essentially checkpointing all the time. That totally kills your disk I/O. Like, essentially 90% of your disk I/O is just checkpointing then. It's super horrible. So this is definitely something on beefy servers where you have to make the trade-off. We just don't do it automatically yet. Perhaps we will in, who knows. I'll tell you other stories in a second. But this is definitely something on beefy servers where you have to say, okay, I accept to like lose 50 minutes of data or half an hour and increase that. We do 50 minutes at SoundCloud by default. Also, like, crashes don't happen so often. And yeah, it's just metrics, right? It's not billing data. So there's this other flag that is extensively discussed in the other talk and even in the discussion. It's so complicated, I won't even explain it. But this is a really, like a setting that is, again, conservative, and it makes only sense on spinning disks. So on SSDs are anyway worse in like writing checkpoints, because they really hate, they hate many things. They hate small writes, but they also hate sustained write throughput, right? So on spinning disks, you can put this number without problems to a really high number, and you should do that. On SSD. On spinning disk, it again depends on your sense of conservatism. This will create more checkpoints. So a complicated issue and very hairy, and this is set way higher with SSD. SSDs are, so this is like what you can get with a really nasty upset SSD. So the yellow curve here is memory series maintenance. So this means whenever, or that often, a memory series was looked at and all the unpersisted chunks were written out to disk. So this should be a flat line. On this server, it's like going up and down like crazy. And like the naive assumption would be when it's at 0, like it's doing nothing, this is when like the checkpoint is running and the disk can't do anything else. Actually wrong. The blue shaded areas, this is when the checkpoint is happening. And at the end, when the checkpoint is done, Prometheus says, checkpoint done, please sync that file. And then the SSD observes, like syncs the file, but then it's super upset about it. So this is, for 10 minutes, it does nothing. It can't even rename a single file. This is also an SSD which is 90% full. And if SSDs are almost 90% full, they are also super upset. So like if you thought SSDs solve all your problems, they create new interesting problems. And like some people even format their SSDs in a way that they don't even partition a third of the space so that they have more headroom to breathe. But this is what you get, like horrible, right? So now there's an elephant in the room. Like people even at this conference ask me, are you crazy? Why aren't you using the page cache? Why are you unmapping files and this stupid checkpointing and everything? There are very good reasons for all of that, and I'm happy to discuss those. It's just too much to explain all of those things in a talk. But you can kind of start with science fiction, like everything in hindsight, we know everything. And we have like infinite brain capacity and coding capacity, and an ingenious person can just lock themselves into the basement for 3 months and just rewrite everything. That would be great, right? So he also sits there. He locked himself in for 3 months and wrote everything new with all those things in mind. And like every single problem I mentioned in this talk will go away. I'm sure there will be a few more new, more interesting problems, but the problems we have here, they are all solved. It's of course still pre-alpha, but watch our communication channels. There will be an alpha soon, and then 2.0 will happen sometime this year, and everything will be great. I'm actually not spoiling any surprises because Fabian will surely give very insightful talks about that, and I shouldn't destroy that surprise. Do we have time for questions? Yes, 5 minutes. I did it. Also, Julius and I will do booth duty at the CNCF booth, which is like there, I think, like in the inner ring. It's difficult to find, but you will see Julius and me. We're kind of tall. So at 3:30, we'll be there, and you can ask questions, but we also have 5 minutes right now. Thank you. So, any questions? Like the FAQ you always wanted to ask, and now you get them good answers in person. Okay, there's one. Yes, please. Have you been, repeat the question, how does this all work with remote storage? My question back is, have you been in Julius' talk 2 hours ago? Okay, you watched the recording. This is exactly the talk you want to watch. And the short answer is, this is all meant, remote storage is always meant in a way that it will not interfere with your local performance. And I mean, this is a basic idea of Prometheus. Your network is on fire. Your Cassandra, whatever you save this to, doesn't work at all, but you self-hosted, self-sustained, single-hosted Prometheus server is still happily collecting metrics. That's the idea. This will remain true. Okay, anything else? I have bonus slides if you're not asking questions. Okay, let me say one thing. This is like, I mean, there were 17 flags, right? We covered like 5 or 6. So the above is kind of interesting, but the lower one, this is something I should have done way earlier. We talked about how the Go garbage collector needs 100% heap growth to start a garbage collection. This is kind of based on a heuristic where essentially all of your heap is like ephemeral, and you have objects coming and going. Then it makes total sense. We have seen that most of our heap is just memory chunks. They stay around for like hours, weeks, sometimes. So it's not what usually you do with heap objects, right? And which will all be solved in 2.0 because it's M-mapped and blah, 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 blah. But you can totally play with setting this environment variable, not a flag, environment variable, Go GT, that tells you how much your heap has to grow to trigger a garbage collection cycle. And we even decided to put this by default to 40 in Go 1.6. And that's what you get on the right. So this is the usual pattern you know. Then I restart the server with the other environment variable. You get the typical go up, and here you have steady state. And you see this breadth or width or whatever, height, is essentially halved, right? So this line, for exactly the same thing, you needed like 27 gigabytes before, now you need 19. Free memory upgrade. I mean, not completely free because you do more garbage collection. That eats another core or something, right? But this is like, you can even do this with your 1.5 server. It's like, I mean, unless you're CPU bound, this is super effective and will be default. You can still set it in the environment variable, but this will be helping a lot. In 1.6, it will even automatically realize, oh, I have more memory, I can have more chunks with the new heap size. So that's pretty nice. This is how it works, right? In 1.6, you have like same machine, just different Go GC setting. This goes up to 10 million, and this goes up to 60 million. With just a few more cores you burn for garbage collection. Okay? Yeah, I think we are out of time. If you have any urgent question, raise your hand now or come to the booth. There's a hand.
Can you explain how the amount of reflex influence the performance?
Okay, this was you saw this flag, right? So this is a weird implementation detail in this storage. We have to kind of lock a time series before we even know its fingerprint. No, whatever. It's more complicated than that. But we need essentially a mutex before we create something in memory. So we have stochastical locking, where we have a limited set of mutexes and round robin them to time series. And that's by default 4,000, which should be just enough. But I have seen scenarios, high ingestion scenario, where this is actually getting lock contention. And then you can set this to higher values, like almost no penalty.
What influence the amount of metrics, like the metrics
yeah, if you have a lot of time and you want to ingest a lot on them, then you get, it just logs up now and then, right? Very shortly. You can play with that. It's an easy one to play with. Okay, meet me at the booth if you want more questions.